Hey folks, welcome back to today's class. What we're going to be doing is starting what many would consider, and I would consider this as well, the most difficult part of the subject, which is about position time graphs. And we'll spend nearly 2 weeks on this, and there will be times that we have to revise to go back onto it, because once you get it, you'll forget it within a couple of days anyway. The important thing to understand about because this is so difficult, is that it is normal to not understand it straight away. Like, it's very rare for someone to just watch this video or a series of videos and just be like, oh, I understand it perfectly. Actually, I don't think I've ever encountered someone like that. So it's going to take a lot of practice. You will make a lot of mistakes. There's some very common errors that happen. But the idea is that things like these videos, you can rewatch, you can pause, and then I'll be there, and any other teacher will always help you through that process as well. So we're going to do two different types of position time graphs over the 2 weeks, but to keep things simple, we're just going to start with one that's a little bit easier, which is displacement time graphs. Now, just a reminder that displacement is a vector, which means that it has a magnitude and it has a direction. Okay. Now, before we get started on what the graph looks like in a scenario or something like that, I'm going to talk a little bit about direction. Okay, so we've talked about, okay, you could go left or right, you could go up or down, you could go north, east, south, and west. These are all valid directions. But when it comes to graphing these positions of an object that's moving, we can only use really two directions, and that's going to be either, I'll put that in blue, for this purpose, it's going to be either a positive or a negative direction. Okay? So displacement can do this. We can have, for example, a displacement of 10 meters, or we could have a displacement of -5 meters. There is no such thing as a -5 meter distance. That doesn't exist. Like, meters are either there or they're not. But when I'm talking about putting a negative in front of something, it just means a direction. Now I'll show you an example that might make it a little bit easier to understand what I am talking about. So let's say we've got this person here, and they're standing at their origin, which we're going to call 0 meters. Okay? We can put some objects around here. That's a tree. Maybe this will be a little house. Okay. And these objects are various displacements from this person. And this person is going to make a journey across what's going on. So let's say that this tree is 10 meters away. And this house is -10 meters away. So it's kind of like a scale. And when we're talking about these things, we're always going to talk about in 2 dimensions. If you do 3 dimensions, it's crazy. You can't wrap your head around it. And just to sort of break it up, let's do something of -5 meters. Maybe this is a I don't know, a bicycle or something. A robot with 2 wheels. It looks like Wally. Anyway, this is just illustrating the point that you have the origin, which is going to be 0 meters, always. You can have objects that are positive away, which is, in this case, is going to be to the right, and you can have a negative displacement as well. And the negative and positive just mean that it is a direction, okay? So these are just directions. There is, I'll just equate these as well. That's a plus, and they just mean direction, okay? So you have to sort of remove some of the things that you might have understood about mathematics, about negatives and stuff like that. I mean, we'll use them, but it's just for a direction, okay? All right, so we've got a little scenario that we're going to use to draw up our displacement time graph. Now, for a displacement time graph, we have to have an x-axis, which we're going to call time. Might make that a little bit, just a smidge longer. So that will be time, and we're going to do that in seconds. It could be hours or days. It just depends on the problem that you're trying to solve. And then we're going to have our y-axis, which is going to be displacement. And we'll put that in meters. Okay. Now, sometimes you don't need a negative part to the graph. It all depends on what's sort of going on, okay, in the scenario. So, this boy, he walks to the tree in 5 seconds. He then waits for 10 seconds. He then walks to the house in 10 seconds. And we've got these distances here. You're not necessarily going to have to draw these graphs straight away. Today is really about interpreting them. But I think just building it up from the base will help you understand a little bit about what's going on. Okay, so we'll do this in red. The boy walks to the tree in 5 seconds. Oh, let's actually get some numbers. We're going to have a 10 here. 10 meters. We'll have a 0. You should always label your axes first, hey? 10 meters. And what are we going to do? We're going to do blocks of 5. So we've got 5, 10, 15. No, that's not going to work. I need 5, 15. Okay, 5, 10. You can probably fast forward this section because it's probably not the most interesting, but that's all right. Okay, so the boy walks to the tree in 5 seconds. This tree is 10 meters in the positive direction from the boy. He starts here, and then he's just going to go straight up. And that's what this first section shows here. So he goes here, right? He's going to this tree in 5 seconds. We're going to say that it's at a constant velocity or constant speed if you're still trying to wrap your head around that word. And that's what's happening. He started at 0, then over the course of 5 seconds, he ends up being 10 meters away. All right? Now, the next part of the problem says he then waits for 10 seconds. So waiting means he's just going to chill there. He's not going to do anything. So he's just going to be stationary. And this is a flat line here, right? And that means he's just waiting. Now, when it comes to a displacement time graph, if you ever see a flat line, that's easy. It just means the person or the object is doing nothing. They are not moving whatsoever. They are staying at whatever displacement they are. Okay, so that always means sort of no movement, all right? So no movement happening here. No movement. Right there. Good enough. Let's do this last one in orange. He then walks to the house in 10 seconds. So he has to, he's just going to kind of wait here for a bit. And then he's going to walk 10, 20 meters in 10 seconds. Okay, so he's going to start from here, and we have to go all the way down there. So the first part, and then the second part. And that's a straight line as best as I can go. Okay, now we'll just finish up a little bit here. This is moving, positive direction, and the orange is showing moving in the negative direction. Now, if you remember stuff that you might have learned in Year 9 maths, these are things called gradients. We will not calculate them today, but we will spend some time later on it. But for this type of problem, that's what this means. Moving in a positive direction, no movement, moving in a negative direction. And that is really the gist, is as much that you need to sort of understand at the moment. Alright, so here's another problem which you're going to have to encounter, which is taking sort of the reverse. So there's a displacement time graph, and in this case, positive means north, negative means south, and it's just of a random object. So this thing is moving through time, and there's the relative displacement. So a normal question I could ask you is, well, when is it not moving? When is it moving in a positive direction? And when is it moving in a negative direction? So let's have a look at when it's not moving. This part here, it's at 200 meters displaced, and for the next, 60 seconds, nothing's happening. Okay, so that is not moving. we've also got here, because it's flat, and it's also flat here. Okay, it's almost like, what is this? So it's 20 seconds, 200 meters. Maybe this person is sprinted, then they stop, then they keep moving, and then they stop, and then they come back. So we've got the moving in a positive direction here. And we've got a positive direction here. And then moving in negative, we've got this person. So they're moving in a negative direction because they're going towards the negative, if that makes sense. All right. Now, a key problem that might happen is if you saw something like this, right? So it comes up like that. And I said, oh, is this person moving in a positive direction, or are they moving in a negative direction? Because it's in the negative axis, right? So does that make it in a negative direction? Well, that's the trick. They are negatively displaced, but they're not going further negative, right? They're moving towards positive numbers. So really, what this means is this is blue as well. They are moving positively, okay? Now, just to rewind all of that, I will show you something else as well. And we'll blot this out just so you can just see that I only want to pay attention to this section of the graph here. So just zoom in. All right. So this person, they're moving positive, then they stop, and then they move positive again. And I could ask the question, well, at what point is this person moving the fastest? Okay, and without any calculations or anything like that, because we will do that another lesson. But when are they moving the fastest? We know that it's not this, because there's no movement happening here. No movement. They're 200 meters displaced, so then for the next, 60 seconds or something, or 50, they're not moving. So it's either one of these spots here. Now look at the shape of the line here and compare it to this one. I could ask you the question, which is steeper? And by steepness, I mean, is it flat or is it super steep? And you probably can see that this is the steepest. The steepest, right there. And steepness means it's the fastest, okay? This is the fastest. The steeper the line, the faster it is. And if you want if you want to jump the gun, I guess, to next lesson, it's to do with, well, how much displacement is actually covered in how much time. We could do that really quickly. This is 200 meters in 30 seconds, okay? 200 meters in 30 seconds. And this is 200 to 500 meters, so it's really 300 meters in. Again, this is 70 to 100. Not even, that's 70 to 80. So that's 20 seconds. 300 meters in 20 seconds. So just by looking at it, you can say it's the fastest. You could break it down mathematically and say, well, this person's at this stage, they're covering more displacement, I shouldn't say distance, in a smaller amount of time. So therefore it's a steeper line. Therefore they are faster here, okay? And they are slower here. Hopefully that makes sense. As always, you can rewind these videos and stuff, try and break it down a little bit more in case you missed anything. Peace out.